Hi, in the previous video we saw a method to identify and evaluate the different types of power losses we have on a MOSFET. So the target for this video is to apply that method in the LTspice circuit we have designed in previous videos. So first of all, when we want to evaluate the power losses of a MOSFET, we have to consider the voltage across the device, this one, and the current through the device, this one. We are representing the waveforms during two switching periods, as we typically do. And in the bottom we have the product of both waveforms, the instantaneous power. So as we saw in the theoretical explanation, here we turn on, let me change the color. Here we turn on the device, the voltage across the device falls, the current through the device rises, and we have a peak in the instantaneous power that we see here. And one difference with respect to the theoretical explanation is this one. We have an extra current peak in the MOSFET. This is something that we will address in the next slide. Then, after we turn on the device, the MOSFET is in on state, is this interval. Okay, we have some current driving through the on resistance of the device, and although here it seems that the instantaneous power is zero, it's not zero, as we will see in a couple of minutes. And then we have the turn off process. We turn off the device here, the voltage across the switch rises, the current through the switch falls, and we have a peak in the instantaneous power. So what we are going to do now is to analyze in detail each contribution to the overall power losses of the MOSFET. So we will start with the turn on process. If we check the turn on transition in detail, we will obtain something like this. Note that this is the voltage across the device, and this is the axis, vertical axis of that voltage. Here we have the same for the current. And as we saw in the theoretical explanation, we have some overlap between both waveforms. So, well, in order to have a reference, this time is around 10 nanoseconds, which is much smaller than the switching period. So now we are going to identify some stages in this turn-on transition. First of all, we can consider that the turn-on process starts here because we have 0 amps. As we saw, the current through the device rises, and at the same time the voltage across the device is constant, so we have overlap. And according to the theoretical explanation, this stage finishes when it reaches the final value. The final value is the inductor current, this level we have here. But in this simulation we see that we have an extra peak. Okay, that peak, that current peak, is due to the diode turn off. When we turn off the diode, we see a current peak in the MOSFET. This is something that we are going to address in another video, but it's called the reverse recovery process of the diode, and it takes place during the turn off of the diode and at the same time during the turn on of the MOSFET. So in summary, what we see is that the current rises, but it doesn't stop here in the final value. We have an extra peak caused due to the diode, and as a consequence we have more turn on losses because we have more overlap between voltage and current waveforms. Then the current through the MOSFET reaches the final value and the transition finishes here. So what we can do now is to apply the method that we saw in the previous video in order to evaluate the power consumption during the turn on. So what we do is we keep the waveforms as a reference here, and we draw here the instantaneous power during that interval. And according to the method, what we have to do first is to evaluate this integral, which is the energy of the turn-on process. We can use LTspice, and as you can see here, we have the information about the integral is 850 nanos. So our next step is to determine the average power consumed during the turn-on. If we consider this energy and we multiply it by the switching frequency, we obtain that average turn-on power losses is 85 milliwatts. Okay, so now we will do the same with the turn off. So now we will focus on this part. The idea is very similar. We check the voltage and the current. We have overlap because we have voltage rising as the current is still positive. Then, well, in this case, we see that the current falls very quickly, but at the end we have some overlap. In this case, as a reference, this time is around 40 nanoseconds, which is also very small in comparison to the switching period. Well, now we will try to evaluate the power losses due to the turn-off process. So we evaluate this integral. This is the energy related to the turn-off process. In this case is 3.4 microjoules, and taking into account that average power consumed during the turn-off is energy divided by the switching period or multiplied by the switching frequency, we obtain this quantity, 340 milliwatts. Okay, and finally we have to do the same for the on state, okay, for this interval. As we said, here the power, the instantaneous power, it is not zero, okay, it's a value that is higher than zero, but is very small in comparison to the axis values we have here, okay, in comparison to the peaks we observed during the transition. But it's not negligible, because it's true that the amplitude is smaller, but the time interval is higher. And the important thing here is the integral. So we go we focus on that on state, this one. Note that this state is T on, which is D times, more or less in our case, is D times the switching period, which is around 2.8 microseconds. So, well, is much higher than the turn on or the turn off. Okay, so it's true that the instantaneous power amplitude is much smaller, but the time is much higher. At the end, what we want to evaluate is the energy related to the on state. So basically we have to evaluate this area. Again, we use LTspice, we obtain the integral value. In this case is close to 2 microjoules. With this, taking into account the switching frequency, we obtain the conduction losses. Is 200 milliwatts. So in this way we have identified in LTspice the three types of power losses for the MOSFET, and we have evaluated the quantities that we obtain in each case. So in the next videos we are going to apply these ideas for other components. So see you